Good morning. This recording is for Pre-Algebra Chapter 8, Lesson 7, Linear Inequalities. Linear inequalities are a lot like linear equations, but instead of equal signs, they have these inequalities. Oop, I got a little overboard on that one. There we go. All right. And it just means that linear inequalities have an infinite number of possible solutions. And remember, a solution is a point on a coordinate plane that makes a linear equation or a linear equation true. It means that when you plug in those points for x and y, it makes the statement true. And it also means that when you have linear inequalities, there's a lot of possible options. So like if you plug in a certain number in for 1, there's a lot of, and for x, there's a lot of possible y's that could make the statement also true. So because there's so many different possibilities, there's so many different solutions, it's impossible to show them all in just like a y is greater than blah blah blah. Alright, so instead we have to show the solution using a graph, which this then just gives us an idea of what the possible solutions are and what they are not. So up at the top we have an example of a linear equation, which for this particular one the linear equation would be y equals down 1 to the right 3. Yeah, down 1 to the right 3, so that would be negative 1/3 x plus 2. So that's the linear equation for that one. Down here, we have a system of linear equations, and that means that we have two equations on the same line, and then the one point where they intersect right there is called the solution for those two lines. For the linear equation, any point on the line is a solution. For the system, only this one point is a solution. And then when we have linear inequalities, down here at the bottom, you'll notice that that there's a whole shaded region. You'll notice that there's a whole region that's pink in this case. And that shaded region is actually where every possible solution to the linear inequality, like that one, and that one can be. So if you plugged in the point 0, 0 on this first one on the left into x and y, you're going to get 0 is less than or equal to x, or excuse me, 0 is less than or equal to 0 plus 2, because that's the equation, and then if you solve it, you get 0 is less than or equal to 2, which is a true statement. 0 is less than or equal to 2, which means the point 0, 0 is a solution. Oops, I gotta wipe something off and I make a huge mess. So the point 0, 0 is a solution, but I could also try the point 2, negative 2 and see if that works. And I'm going to get y was negative 2, x was 2, and I'm going to get 2 plus 2 is 4, negative 2. Well, negative 2 is definitely less than or equal to 4, so it's definitely a solution. So as you can see, there's an infinite number of solutions. Basically, anything below this red line is a solution, and that's the shaded region. And we know whenever we have a shaded region, those are where possible solutions, or where solutions are to this particular linear inequality. Now, as you'll notice between the linear inequality on the left and the linear inequality on the right, the linear inequality on the left has a solid line, whereas the linear inequality on the right has a dashed line. And you'll notice that the big difference is because this one has a less than, and this one has a less than or equal to. So whenever you have an or equal to, you have to use a solid line, because any point on that line could also be an answer. I could use the point right here, 1, 3, and even though it's on the line but not on the shaded region, it is a solution. The only thing is if I have the not or equal to situation right here, like the point 0, 0, the point 0, 0 is not a solution for this, because if I were to plug it in, 0 is not less than 0. And since it's a false positive right here, it basically just says this boundary line, if it's dashed, it does not include the solutions, but anything immediately where the shaded region starts. is a solution. So if I were to move over just a fraction of a hair and to measure things in like halves or whatnot, and I have the negative 0.50, and I plug that in, I would get a true statement because it is in the shaded region, not just on the boundary line. And then also, if you see this point 1, 1, notice how it's not in the shaded region, and that means that it's not a solution. So if I were to plug this in to here, I would get 1 is less than negative 2 times 1. Well, 1 less than negative 2 is a false solution, which is why it's not in the shaded region. Okay? So again, the boundary line, which happens in inequalities, is basically telling us the furthest point that could be a solution. And if it's a solid line, it means the dot on that solid line can be a solution, whereas if the line is a dashed line, it means that it can't be a solution exactly on that line. But then again, every place where it's shaded does have a possible solution. So let's go ahead and talk about graphing. And then notice the shading inequalities. Oh, and then I talk about points that are solid line, dashed line. All right, we talked about that. All right, so what if you need to actually graph? We talked about just looking at graphs, but what do you need to do if you need to graph? Well, the first thing you need to do is to graph the boundary line as if it had an equal sign. And just remember that it's more than likely either going to be in standard form, which we haven't quite talked about yet, but you'll see in the next slide. And then there's also slope-intercept form, which I know you know about because it's from 2 videos ago, and we're going to use it to help us graph. And just remember that if it's less than or greater than, less than or equal to, or greater than or equal to, it's a solid line, and that if it's greater than or less than, it's a dashed line. And then we're going to test a point to figure out where the shading goes, and then from there. So let's go ahead and graph this line. Y is greater than negative x plus 3. So the very first thing we know already is that it's going to be a dashed line because of that. Okay? Because of that, it's going to be a dashed line. Now, if it had the or equal to bar underneath, that means that would be a solid line. But it's going to be a dashed line when we graph. All right? So what's the next thing we need to do? Well, this is in slope-intercept form, which means y equals mx plus b, or in this case, y is greater than mx plus b, and the b, in this case 3, is going to be my y-intercept. So I'm going to put a point at 0, 3. All right, the y-intercept, 0, 3. And then from there, I'm going to use the slope, which is negative 1, which means I'm going to go down 1 to the right 1, because what's negative 1 as a fraction? Negative 1 over 1. So I'm going to go down 1 to the right 1, down 1 to the right 1, and then I'm going to connect my dots. There you go. And I could also go up 1 to the left 1, up 1 to the left 1. But it's just the opposite of down 1 to the right 1, and it actually ends up being on the same line. It's just going the other direction. All right, so now I am, and just remember it's dashed, and I'm going to go through and just use the eraser tool to cut it up. And you can do the same thing if you're doing this on the iPad, or even if you're doing it on paper. Even if you accidentally draw a solid line instead of a dashed line, just take your eraser to it and draw some holes in your line, and then it'll be dashed. Okay? So now we're ready to go ahead and shade, and that means we got to test a point. We need to pick a point that's not on the boundary line, because again, if it's a dashed line, it's definitely going to work, and if it's a solid line, it's going to work every single time. So we need to pick a point not on the boundary line. Now, as long as 0, 0 is not on your boundary line, I recommend using it, because 0 is really easy to add and really easy to multiply by. All right? And so since 0, 0 is not on my boundary line, I'm going to go ahead and use it as my test point. And I'm basically going to plug in 0 for y and 0 for x. Now, you might have missed that. Let me play it again. I'm going to plug in 0 for x and 0 for y, because that's the point. Plugging this in should either tell me if I've got a true statement or a false statement. So if you go ahead and simplify, I'm getting 0 is greater than or equal to 3. But that's not true. That's false. So the thing is that if we have a false statement with our test point, we actually have to shade the side of the line where the test point isn't. And that's if you get a false statement. If we got a true statement, then we would shade where the test point was, because the true statement side is where all of my answers are going to be. But for this particular situation, because my test point was false, I'm going to shade where my test point isn't, which is over there, okay? And then you can just go ahead and erase your test point. All right, That's next. All right, oh, and so anything in this orange area is a possible solution. 3 is going to work, hopefully. So if I replaced x with 3 and y with 3, I'm going to get x is greater than 0, which is true. So that is, again, just one little point that's in the shaded region that does work as a solution. Okay, word problem time. All right, so apricots cost $3 per pound and tomatoes cost $1 per pound. Suppose you want to buy apricots and tomatoes. You plan to spend no more than $10. How many pounds of each can you buy? Now, if the equation isn't in y equals mx plus b or slope-intercept form, you're going to have to solve for y first. And this is an example of an equation that starts out in standard form. So I'm going to go ahead and make, oh, and don't forget that when you're solving for y, since we have inequalities, you could have flippage. So just pay attention to that, okay? Because the flippage would throw off your line if you don't remember it when you're supposed to. All right, so I'm going to make A the number of apricots that I can buy. I'm going to make T the number of tomatoes I can buy. And I know that $3 for each apricot I buy. So if I don't know how many apricots I'm buying, but multiply it by 3, I'm going to get the amount of money I spent only on apricots. And then if I add the number of tomatoes I buy times the price of the tomatoes, I'm going to get the amount of money I spent only on tomatoes. Add them together, and the thing is I can't spend more than $10. I can spend exactly $10, right? So it's or equal to, but the amount I spend on produce, that would be apricots and tomatoes, has to be either less than or equal to the amount of money I have, because I don't want to owe the farmer or whoever's selling me my produce money, right? So I have to spend the money I have or less than the amount of money I have, all right? Now you could have made, now we're ready to graph, kind of. Once you figure out what's going to be your x and y axis, in this case I made apricots my x-axis and tomatoes my y-axis, that basically means that apricots is now x and tomatoes is now y. Which means if I need to get y by itself to get it into slope-intercept form, I'm really getting t by itself in slope-intercept form, okay? So I'm going to go ahead and do that, and I'm going to minus 3a on both sides. And technically 1 times t is just 1 times t, and you really don't need to divide by 1 on both sides, but I went ahead and did it. So t is less than or equal to negative 3 over 1a plus 10. So if I'm going to graph, I'm going to start at 10, and then I'm going to go down 1 to the right 3, down 3 to the right 1, down 3 to the right 1. All right? Now that just went by really fast. So let me go back a little, okay? So now that I have my line, just starting at 10, going down 3 to the right 1, down 3 to the right 1, down 3 to the right 1, I'm ready to do a test point. Now, again, since 0, 0 is not my test, is not on my boundary line, I can totally use it to test. So the thing is if I don't buy any apricots and I don't buy any tomatoes, I haven't spent any money. I haven't spent any of my $10. So basically, I should probably get a true statement because it means I spent less than $10 if I didn't buy anything. All right, so I end up getting this part shaded, and that's my answer. Now, again, any point in here could be a possible solution. I could buy 2 tomatoes and 2 apricots and spend less than $10. I could buy 1 apricot and 6 tomatoes and still stay under my $10. As long as I'm on the line or underneath the line in the shaded area are all possible solutions where I stay within my budget. So if I asked you guys to write a sentence about this or about a possible solution, you'd say, well, I could buy 1 apricot and 6 tomatoes and stay under my $10 budget. Make sense? Okay, let's move on. All right, so last word problem, but not the last slide. Adult tickets to the school play cost $4. Children tickets cost $2. Your goal is to sell tickets to sell enough tickets to make at least $30, which means you'd be happy if you made more than $30, but if you made exactly $30, you'd still be happy. Okay, so we're going to let X be the number of children's tickets sold and Y be the number of adults' tickets sold. Now, whenever they tell you which letters to use, you should use those letters, all right? You might be tempted to use A for adult and C for children, but since they're telling you they want X to be children and Y to be adult, go ahead and use them. And yes, please use them. right? And we're going to graph the linear inequality to show how many of each type of ticket were sold. So if $2 for X number of children's tickets and $4 for Y number of adult tickets has to be greater than or equal to 30. Again, if I make exactly $30, I'll still be happy. But if I make more than $30, I'll be even more happy. So that's why the amount that we make off the tickets needs to be greater than or equal to 30. All right, so I'm going to solve for Y so I can get this into slope-intercept form, and then I'm going to be ready to graph. So there we go. So the only thing is that graphing half numbers is really hard. All right, and the thing is actually in the real world, you're probably not going to sell half a ticket, but we need to keep it that way because otherwise we're not going to have our minimum amount. All right, so I'm going to go ahead and graph 7.5, which is roughly right there. All right, it's really hard to see, but it's in purple there in the graph. Then I'm going to go down 1 to the right 2, which is again really hard to see, but there we go. Again, I probably shouldn't have made my tickets by 2s, but there you go, live and learn. So I'm going to connect the dots, and it is a solid line because I could make exactly $30 and still be happy. But now I'm ready to shade. Now I can test 0, 0, but more than likely it's going to be false because if I don't sell any tickets at all, am I going to make any money? No, least of all $30. So I can, for this one, I probably didn't even need to test a point, but I'm going to. 0, 0, not going to work. $0 is not greater than $30, so it's false, so I need to shade the other side of the line, which means any point in that shaded region works. So if I sold 10 children's tickets and 6 adult tickets, I'm going to make more than $30, which is pretty nice. Now, if I wanted to make exactly $30, then I wouldn't even have the inequality because it would just equal $30, and it would be anywhere that's on that orange line. But since I don't mind making more than $30, any of the combinations that are in the shaded region work. All right, last thing I need to talk about is systems of linear inequalities. Two linear inequalities are graphed on the same coordinate plane, but be sure you shade one boundary line before graphing and shading the second, because otherwise you might get confused where your lines are, and you might not shade correctly, and then you don't get a correct answer, and then your life is a little scary. So just make sure you do one boundary line, one shading, and then the second boundary line and the second shading. Now, the cool thing is that the area where both boundary line shadings overlap, that is the solution range for both linear inequalities. So if I said, find me a point that works for both linear inequalities, you want to find a point where both of the shadings are. All right? So, and make sure that when you're doing this on paper, you either use highlighters or colored pencils. Don't use Sharpies because the Sharpies are going to completely bleed through the paper, and if you need to use the backside, it's going to be completely nasty. So again, highlighters or colored pencils. I should have a few for you when you need them. Okay, let's move on to the next one. Let's graph these two linear inequalities. So my top line is going to be purple, my bottom line is going to be blue. You guys should be expert at graphing these by now. So I'm going to go a little quick. So y-intercept is 0, -5. Slope is up 2 to the right one, or down 2 to the left one, or no, up 2 to the right, down 2 to the right one, or up 2 to the left one. There we go. So it's a purple line, and I'm going to go ahead and test the point 0, 0, and shade because it's false. So the purple side is up below it because we shouldn't shade where 0, 0 is. Now I'm going to graph the blue line, which doesn't have a y-intercept, which means it's 0. So the y-intercept is 0, and the slope is 1/2. So I'm going to go up 1 to the right 2, up 1 to the right 2, or I could go down 1 to the left 2, and I'm going to shade. I can't use 0, 0 because 0, 0 is on the boundary line. Oh, and also remember, it's a dashed line. All right, but again, I can't use 0, 0 because it is on the boundary line, so I'm going to use the point 1, 1, which means 1 for y, 1 for x, and it ends up being false. So I can't shade where 1, 1 is, which is why I'm shading beneath it, and the area where the purple overlaps with the blue is a solution for both the purple line and the blue line. So, and sometimes I like to go over it and make it more prominent, which means if I test a point in that like grayish area, it'll be a solution for both. So if I use the point -3, -3, which is a solution for both the purple area and the blue area, it should work. All right, so both of them work. Now, if I said, what's a solution for neither of the lines, I would pick an area where the white is, because that would be a solution that neither works for the purple line nor the blue line. All right, guys, I'm done. Sorry it was so long.